I wanted to introduce Neha. She's a key member of our team and will be co-presenting in this one. So what is it that we want to say? We want to say that there are two very important technology pieces that so far is unconnected. The Linux networking stack, I say that if someone wants to use a new synonym or someone wants to explain what ubiquitous means, they can say, think of something like Linux. So if a computing device is doing something useful, it is probably more than likely that it is running Linux, whether it is running it here or it is running in Mars, it does not matter, as you all know. It has a mature API for hardware offloads through vendor drivers. There's switch step, TC, there's a lot of that. The TC abstraction is definitely powerful, and with TC, what we were able to do with our project, and I'm sure some of the other hardware vendors have also been able to do this, is because of the consistency of the abstraction. One is able to build a digital twin. One can build it in software first, and without a lot of reinvestment on the code, they can build build it in hardware. And then, of course, comes P4. We are not in Mars quite yet, but I want to say that it's a very, very important language, standardized language for describing data paths. It can be used in hardware, but it can be used in software also, as some of my previous slides show. This P4 support on XPUs, it's happening. It's AMD is doing a lot. Intel is also doing. The Intel IPU ES2100 support is available. And the large consumers of NICs, I think they value at least some level of P4, if not for the actual implementation, then at least for a great, meaningful description of the network. Remember, one of the value proposition of P4 is it kind of takes away the power of the hardware vendor to expose some constraints and then forcing you to build your network based on that constraint. Instead, P4 takes the abstraction higher up, where you can start from a high-level view of the network, and then you can challenge the vendor, go and show the support on your hardware. So that's actually a great value. And we're coming up with newer use cases. Some of these I have discussed. We also have new kind of platforms coming up that is loosely called smart switch, which is generally very high-speed switch in front and an array of either IPUs or DPUs or other kind of NICs at the back. And some of these use cases are enabled through the Microsoft Dash, and I think we have a presentation on that today also. But so far, these two very important technologies, they remain unconnected, and we try to build a bridge. And P4TC is that bridge for growing this network programmability ecosystem. It gives enthusiast, whether a student or someone just getting into this field, to try out something on simpler platform without immediately getting into powerful hardware cards and servers and all of that. So what we have here is you are going to define the data path using P4 and then use some kind of a Linux kernel native implementation of that. The main value that we see is some of these mundane developer knowledge of how to do things at the levels of bits and bytes. Some of these get moved up and automated into the compiler. So we have a knowledge shift from low-level skills, kernel, with this, whether API A is the best choice or B is the best choice. From that, we are doing a knowledge shift towards systems, a knowledge shift towards P4. There is no upstream effort. There is a same interface for either software or hardware data path, this concept of digital twin that I keep talking about. And so, as I briefly mentioned in my previous presentation also, it's based on the Linux TC or traffic class uh, interface. It's a TC-based kernel native P4 implementation. We, of course, worked with a lot of really experienced kernel developers. We have some of them here, Jamal and Anjali and others. And we looked at all of these and looked at what we can do better in terms of achieving kernel version independence, in terms of control plane transaction rate and latency, as well as P4 architecture independence. I mean, currently PNA is the target, but there is nothing blocking it from being applicable to other types of architectures also. The Intel P4 compiler team actually produced a compiler backend for this effort, which generates TC scripts files for the TC kernel support. I think this slide, again, this is not the latest version, but this slide says everything that I just did. So let's now get into the details of how exactly this works. And for that, Neha, please come in.
Hi guys. So I'm going to look here, but I expect everyone to look over there. So by now we know what P4TC is, why it's important. In next few slides, we're going to delve into the software and the hardware architecture, a very high overview, and then to the crux of my presentation that describes how at Intel we use this technology. So here, what you're seeing on the screen, before even we get started, I do want to emphasize that majority of the software work is done by Jamal and his team at Mochatatu. And for the hardware, we have a community meeting where the vendors come together and discuss the best possible solution for everyone. Okay, for anyone who doesn't even know what we're talking about, I'm going to summarize things for you right now. So you have a P4 program and you have a compiler, and the compiler is going to generate some artifacts. These artifacts are fed into some infrastructure code. Now, the only job of this infrastructure code is to entertain the CRUD operations coming from the upper layer and program the target. Target can be software or hardware. So that's that. That's the crux of it. But if we look at this diagram, what it's showing is the main components in the software design. So on the top left, you have a P4 program that is fed into a compiler. The compiler has a P4TC backend in this case. The P4TC backend is going to generate 5 to 6 files. Two of those files are eBPF program that include the logic for the parser, the control block, and the deparser. And these programs are then compiled into eBPF bytecode and then loaded as an action when we do a TC filter add. On the top, the green portion, you also see an introspection file. So for folks who are familiar, this is very similar to P4 info. It's just a mapping. It maps the name to a specific ID. And then in the red, you see some templates. So this template is a bash script, and it is written this way to make it very familiar to folks who are native to Linux. So this bash script, in essence, it will manifest your P4 program in kernel. So think of it like when I run this bash script, there are objects instantiated. You have an empty table in the kernel ready to hold your rules. So if we add hardware to this mix, the again, we have to take the compiler. The compiler will have a vendor backend over here. And then we are going to the vendor backend is going to generate very vendor specific code. I'm going to touch on that, what it means at Intel. And then this blob information will do similar things to what we have in the template. It's going to manifest your tables and empty tables in the hardware that are then ready for CRUD operations. So with this information, we'll touch on the runtime aspects of things. So please assume at this point, step number one, please don't. Uh, uh, at this point, we're going to assume step number one. Uh, Sorry, I'm getting very distracted with that. At this point, in step number one, assume that the template has been installed and there are few rules in this blue box over here. Now at runtime, when the packet comes in, we have hook points that is going to trigger the eBPF code. The eBPF code is going, the first, the parser code will be instantiated, which keeps a header ready. And then the control block code is instantiated, which is going to do whatever your pipeline specifies. Anything that the eBPF code, so that if you would have noticed, your table information resides here, right? So while implementing the control block, anything that your eBPF code needs, it's going to request it from the TC domain. And it does this using kfuncs or kernel functions. You also see your XDP block over here. I think the point of this block is to emphasize that you can have a parser here, you can have your control block running here, and your rules reside in the TC domain, and everything will work perfectly fine. Now, if we consider the hardware offload path, we're taking advantage of skip hardware and skip software flag that exists today as part of the TC kernel infrastructure. So it does exactly what the name says. Skip software, you're telling the kernel, hey, I don't want you to put anything in the software. Skip it and give this information to the driver. Now, the driver again is vendor specific implementation. The driver's job is to take this information and then program their underlying hardware. Now, in the next slide, I'm going to zoom in into this box, how the driver architecture is for Intel devices. Okay, so I am going to repeat some things over here. Um, this is a P4 program. It is a very simple P4 program. It is fed to a compiler. In the case of offload, it's going to generate some artifacts. So step number one is to write your P4 program, compile it, generate the artifacts. Step number two is to take the vendor specific blob, load it onto your device. So at this point, you have manifested your pipeline in your hardware, but it's empty. Step number three is to run the template file. So if you look at the template file, I just said that it is a bash-like conversion of your P4 program. So what it says is P4 template is a keyword. It is navigating to your specific table. It has a table ID 1 and MAC address 48 bits and specific actions. So we take this information. So step number three was to load the template, right? So once you load the template, everything is ready to go. So as a user, I'm going to add a rule and I'm taking advantage of the skip software flag over here. So I'm telling that don't do anything in the software, give it to the driver. So kernel will then give the information as part of NDO ops, and the structure looks very similar to what we have over here. It has all the information that the driver would need to identify a pipeline with the pipeline ID, a specific table within a pipeline with the table ID, and the command is the one, which one of the CRUD you want to perform, and then the entry information. This information is given to an ops layer. The purpose of this layer is to differentiate between different P4 table types. It is then given to this target abstracted software layer. This layer is very flexible. The code over here can be shared between user space, kernel space, Windows, Linux, ESX, you name it. And then it is given to this green portion, which is a very device specific code, target specific code, and your rule propagates over here. So that's the flow of how Intel drivers would perform this operation. And I do want to emphasize that everything that you see on the slide is functioning code today. Everything exists in code today. And I do want to zoom in into the switch dev portion over here. So, so this slide looks complicated for no reason, but you just have to listen to me. So in essence, what SwitchDev does is, so it is common sense engineering that anytime you want to provide an abstraction, you will have a generic API under the hood. They can have some specific APIs, right? That is in essence what SwitchDev is, but it is to propagate from the hardware. The kernel will get a feel that it is controlling the hardware. And from the CSP's perspective, they like it because they don't have the vendor lock-in, and which is also the reason that we at Intel care about enabling it. So SwitchDev has a concept called port representer. As the name implies, it is literally a port representer. It is representing a port. It can be a virtual port or a physical port. Uh, oops. Okay. So it can be a physical port or a virtual port. And from the controller's perspective, it is talking to these port representers, and under the hood, the driver does the job of mapping this representer to the appropriate VF or a PF or an SF. So, and the reason this use case is important because once the controller learns how to program, they can then instantiate a rule add using the TC framework or some user space application that they have. Um, so I'm going to give it back to Deb to go over some of the compiler details.
Thank you, Neha. Just have a couple of slides for those of you who are not intimately familiar with the P4 compiler. Most of the compilers have two distinct phases. One is the front end, and one in the front end, all the lexical and syntactical analysis are done, and in front end, all the optimization and target specific code generation is done. P4 compiler introduced mid-end, where you can do some level of platform specific optimization in the mid-end also. And then, of course, there is this traditional backend. So as you can see, it starts with a P4 program. The front-end part is unchanged. We are using the same open source P4 compiler front-end and mid-end also. And there is a vendor-specific hardware backend and a hardware target binary that can be actually deposited on the hardware. Here we have one more twist, which is so because of this digital twin analogy that we are always trying to maintain, ultimately, every time the compiler is invoked, it will produce both the hardware blob as well as the necessary software functions, software information. So the software information will have that introspection file, which is similar to P4 info, and that can be loaded through netlink to run on the kernel. So the same P4, you have the flexibility of using some of these skip software and skip hardware type of flags that Neha mentioned. You have the ability of either running it in software or running it on running it hardware assisted. These are some of the output files that are generated, and I think Neha already touched on this. There is the JSON file input that we call the introspection file. This is used for programming the control plane. There is a template file that is essentially a shell script and has template definitions for different types of P4 objects, etc. There is a eBPF parser C file and control block C file, and then there is also the eBPF header. These are generated every time the compiler is invoked. So that's all that we